everyone, welcome to this next video on polynomials and factoring. You can see the objectives listed below. Each of the screens following this one are going to talk specifically about each of these objectives. So I would not write them down right now. I would write them down as you go in your notes. So let's get started. So as you can see here, we have a graph, a polynomial graph, and it has several characteristics. We see that on this side, the end behavior is up, this end behavior is down, and it has 1, 2, 3, 4 zeros, or x-intercepts. And on some of these x-intercepts, the graph crosses at that 0. So it changes from positive, the y-values change from positive to negative, and it doesn't linger. This is a cross. Sometimes, however, at the 0, it goes up to the 0 and back down. So it goes negative, goes to the 0, and stays negative. This is a bounce. Here you can see that it will eventually cross at 2, but it wiggles a little bit first. So this one is a 0 that does slightly different behavior. It does cross, but it wiggles first. It lingers. Here is just a basic cross, changing from positive again to negative. Right? So this is the polynomial. And so what we want to do is we want to factor it using its graph. And so we're going to write its x-intercepts. So there's an x-intercept at -3. There's an x-intercept at -1. There's an x-intercept at 2. And there's an x-intercept at 4. All right, the multiplicity of zeros. Well, what that means is, since this is a cross, the multiplicity is 1. And since at -1, this is a bounce, the multiplicity will be 2. And at 2, this was a wiggle, the multiplicity will be 3. And then at x equals 4, that was also a cross, and so the multiplicity will be 1. Well, how does this work? Well, let's write the factors. The factors are x plus 3, right? You get a factor by setting it equal to 0 to get the 0. And this would be to the first power. The bounce would be x plus 1, there's the factor, and then the bounce would be to the second power, right? So the multiplicity tells me what power that factor is. And so then this would be x minus 2, which is a wiggle, so that'd be to the third, and then x minus 4 to the first. Now, if I'm going to write a polynomial, I have a function. I have this letter a. Letter A, which we'll talk about in the next screen or two, talks about the end behavior. Since this function was going up and then down on the end, this particular A is going to be negative. But we'll talk about that later. So I'm just going to put an A there for a placeholder that talks to end behavior. And then I'm just going to write my factors. So I have x plus 3, x plus 1 bounce, so squared, x minus 2 wiggle, which is the third, and another cross, which is to the first. And that's a possible equation, a function for that polynomial graph. Sometimes polynomial graphs do not have x-intercepts, or they have x-intercepts that are not at whole numbers, like the factors we saw earlier. So for instance, if I have x squared plus 4 equals 0, right, and I were to solve for x on this problem, I would have x squared equals -4. Well, to take the square root, you would have plus or minus the square root of -4. Well, remember the rule, it's not a real number if you're trying to take the square root of a negative number. So this is actually x equals plus or minus 2i. And so the square root of -1 is I, and then the square root of 4 is 2. And so you would have 2. But the thing I want you to notice here is that they happen in pairs. They always happen in pairs. Non-real factors always happen in pairs. And what this looks like is a graph, a polynomial graph. A polynomial graph where it doesn't cross the x-axis. So it looks more like this. Now, if I were to apply the same process here, I would have x squared equals 5. And so it's positive. It doesn't have an I in here, but it's once again a pair. It is plus or minus the square root of 5. And these always happen in pairs. These always happen in pairs. So if they only list 2i, you also know that negative 2i is a factor. If they only list this negative square root of 5, you also know that square root of 5 has to be an answer. And the square root of 5 is about 2.25. So it does cross the x-axis. It just doesn't do it at a whole number. So if you had a problem like the one below, where it says find the degree of polynomial with the following zeros. So what we want to do is count up using multiplicity, count up so that we can talk about what the degree is. All right, so for instance, x squared over here, x squared is a degree 2 polynomial. X to the third is a third degree polynomial. So it's whatever the highest power is for that polynomial. And what they're trying to get at here is, do you remember that some of these factors come in pairs? All right. So for instance, it says negative 2 multiplicity of 2. So that would be degree 2 polynomial. 0 multiplicity 3, that's 3. 2i multiplicity 1, well, this comes in a pair. So it's not only 2i, but it's negative 2i. So this would be a 2. This is square root of 5. Remember, it comes in a pair. So negative square root of 5 would also be a factor. That's 2. So when you add this up, you would have 6 plus 3. So this is a 9th degree polynomial. 9th degree polynomial. Now, another one that's really common that they'll do is they'll say x squared plus 16 equals 0. And so x is going to be plus or minus 4i. So if I saw a factor here, right, for 2i, the factor, if I'm writing it out, is going to be x squared plus 4. And that will get both factors. So here, this is going to be x squared minus 5. So that's the factor. So here, this is going to be x plus 2, multiplicity of 2. This is 0. So x, multiplicity 3, and then these. These are my factors for that degree polynomial. So once again, here's an example on how you write the function. And remember, some of these things come in pairs. Some of the factors come in pairs. So I always start off f of x equals and then a. And we haven't talked about in behavior, but we will. All right, so it says here are the following zeros. So it just says it doesn't have multiplicity here. But I know that if I had negative 2, this will be x plus 2. Right? This is 3. So this will be x minus 3. This is 2i. Well, remember, if I were writing it like this, I could write it x minus 2i and x plus 2i, unless I remember that this is just x squared plus 4. So I could write either for that one. And then square root of 3, that's going to be x plus square root of 3, x minus square root of 3, or I could remember that this is x squared minus, because it's real, minus 3. So you can always write them separately because they always come in pairs. Some of these always come in pairs. If it's not real and it's irrational, it does not. They always come in pairs. These, however, if they're whole numbers, do not come in pairs. So on this screen, we're going to begin to talk about in behavior, this a that's at the beginning of all these polynomial functions, this a. And it's the idea that some functions, polynomial functions, are even. In other words, they're symmetric around the y-axis. And so you can see here anything that's going to be to the second power, to the fourth power, to the sixth power, all of those functions have the potential to be even. Okay? Odd functions are functions that are symmetrical or have symmetry around the origin. So if we rotated around the origin, you'd get the same function. And these are considered odd functions. And you can kind of see the end behavior. On an even function, they're either going to both be up or they're both going to be down. And on an odd function, the end behavior is going to be down and up or backwards, right? So if there's no symmetry, even an odd symmetry, then most graphs are going to be neither. I mean, that's just the way they are. Most graphs are not symmetrical at all. So it's a rare thing that you would have a symmetrical polynomial, Most of them will not be. What we're looking at, however, is the end behavior. What is the graph doing at the ends? So now I want to begin a discussion on end behavior. And so we talked about even and odd functions in terms of symmetry. But now I'd like to talk about even and odd in terms of degree. So the degree of a function. So for instance, if you had x squared, the degree of the function would be even, right? And if I had x to the third, fifth, seventh, whatever, the degree of the function would be odd. Now this is not symmetry necessarily. Remember that most polynomial functions are neither even or odd symmetry. But the power itself, 2, 4, 6, 8, is an even power, and 3, 5, 7, 9, and 1 is an odd power, and that speaks to its end behavior. All right, so for instance, if I had an even degree function where a is positive, the end behavior would be up, up on the ends. Even degreed functions are always the same direction on the ends. Right? So if it was an even degreed function and a is negative, then it would be, both ends would be pointing down. All right? An odd degree function like x to the third, x to the fifth, x to the seventh would be up to the right, down to the left. If a is negative, that just switches. So it would be down to the right, up to the left. So this speaks to end behavior of a polynomial function, and it relies on the number or the even or oddness of the degree, not the symmetry. So this will be important when we, on the next example, sketch a polynomial. Okay, so find the zeros and sketch the graph. All right, so we're looking here at multiplicity and factors. So the multiplicity, if we look here, the factor is going to be at x equals -1, and it's going to be a cross there. And at x equals 2, that will be a bounce. And at x equals -3, that's going to be a wiggle. Now, the end behavior says that this a in the front is going to be positive. So since a is going to be positive, we know that if it's an even powered function, it's going to be up, up. And if it's an odd powered function, it's going to be down, up to the right and down. All right, so let's count then. We have 1 plus 2 plus 3 is a 6th degree polynomial. So this is a degree 6, which is even, and an even number. This is an even number, not an even function. All right, and it's positive. So that means it's going to be going up, up on both ends. That tells us how we're going to draw our graph. All right, so we're going to put in our values. This is -3, this is -1, and over here is 2. And we're going to start at the top, and it's a wiggle. So I'm going to change colors. I'm going to start at the top. I'm going to wiggle a little bit here. At -1, it's a cross. So I'm crossing at -1. And at 2, it's a bounce. And I remain up, up. And that's the sketch. So this is a positive, even numbered polynomial. And this is my sketch. Now it's not exact, but that's close enough and that's sufficient. So here it is in a slightly different form. We don't have a graph this time, we have a table. And in this table we can find out the same kind of information. We just have to do it numerically. So one of the things we wanted to look at before we graph it is we want to look at the table, right? We want to look and see what we can tell about the table. So we know it's ordered from -4 to 4 on the x-axis. And then these are selected y values for those x. And so this y value is going to tell us a lot of information about the graph, right? We can look here and we can see that the y value is 0 here, here, and here. These are our zeros. Those are the x-intercepts, right? Because y is 0, we've got x-intercepts, and we have 3 of them. Well, we want to look at the behavior on either side of them. And we can see that we have positive on one side, negative on the other, right? So we kind of know that it's going to be at least a cross. How do we know if it's a wiggle? We know for sure it's not a bounce. What would a bounce look like in a table? Well, a bounce would look like if I had negative on one side of the 0 and negative on the other side of the 0. So from a table, there's a lot we don't know, but there's a bit we do, right? And then here's another 0, and it also changes. So we either have crosses or wiggles. We don't know for sure, but we know we have at least that. The other thing we can determine is the end behavior. This value right here is going up. This value here, down. At least it looks like it's trending down, right? You can see that. So we have on one side going up and we have the other side going down. So if we want to sketch a quick graph, right, we would put in the zeros and we would put them at -2, 0, and 2. All right, and here it's going to start up, but down here it's going to start down. So I'm going to go down, cross. I'm just going to add a little wiggle here, and then cross. So this is an odd degree function, and I can tell it from the table, and which means right here it could be an x to the third, unless I added a wiggle, right? And then that would be x to the fifth, which it could be. So either way, you could write that down, and that would be a possible graph. Now, I don't really know what A is, but I do know that A has to be what? Positive or negative? Well, it's an odd degree function, and it goes up to the right, so it's going to be positive. So this would be a positive A, and then writing out those. And whether it's a wiggle or a cross, I can't really tell from this table, so keep that in mind. So here is a homework problem. I want you to graph the following using what we talked about in this video, in behavior and the multiplicity of zeros. I want you to have this in your notebook. I want you to highlight it. I want you to make sure that you show it to me when I go to check notebooks so that you get credit for it. And then when you go to class next, the day after this video was assigned, go at the first of class, go to the board and put this graph, your graph, on the boards. We'll probably be doing other problems as well. All right, see you then.